Welcome back to the 13th live session of Solar Energy Engineering and Technology. Myself, Soumya Tiwari. I am PhD scholar at Department of Sustainable Energy Engineering at Kanpur. So, this is an extra session that we have scheduled for doubt clearing session. So, what we'll do in this session is uh, we'll solve some numerical problem through from the topics throughout this course. Hello. Okay. Let's start the session. So, welcome back to the extra live session of this solar energy engineering and technology. Myself, Soumya Tiwari. I am PhD scholar at Department of Sustainable Energy Engineering, IIT Kanpur. This is an extra session. We have covered all the doubt session regarding each of the weekly module for this particular course. In this session, what I'll do is I'll basically give you a question, basically numerical problems from topics throughout the course, and I'll also solve them as a tutorial for you. Okay, so let's start the session. So this is the first question. I'll read the question aloud for you. So we have to calculate the hour angle at sunrise and sunset on June 21st and December 21st for a surface inclined at an angle of 10 degree and facing due south. The surface is located at Mumbai, whose latitude and longitude angle are given. So I'll give you a few minutes to think on this question and then we'll solve this question. Okay, let's see this question. So, okay, we have to calculate hour angle at sunrise and sunset. Okay, on June 21st and December 21st for a surface inclined at angle 10 degree. So we have a angle surface inclined at 10 degree and facing due south. Okay, so your azimuth angle is 0. Now this surface is located at in Mumbai, whose phi and latitude and longitude value is given, right? So if you talk about June 21st, okay. So what we know about June 21st is declination angle will be, if you remember, it will be 23.45. Other way to calculate this value is you can calculate the value of n, which will be 31 for January, 28 for Feb, 31 for March, 30 for April, 31 for May, and 21 for June. And you can add this number and then you can calculate declination angle, which will be 23.4. So let me raise this. Okay, okay. So it will be, then you can calculate. Okay, what's happening here? Declination angle by this formula 23.45 sine 360 by 365 284 plus n, right? We will calculate by this formula also. The value will for June 21, if you remember, summer solstice and winter solstice. So it's on summer is on solstice on June 21 and the winter is on December 21. So for December 21, what we have declination angle is, it will be your for December it will be minus 23.45. Okay, so declination angle varies between plus 23.45 to minus 23.45. Right. Now, if you remember, for horizontal surface, if you want to calculate the hour angle, right? So we knew the formula cos omega s was minus of tan phi, right, into tan delta. But for tilted surface, if you are talking about tilted surface, and that too facing south, so we have one formula which is so basically it's mod of omega s t. So t is for tilted. It is minimum of one of these two values. So mod of cos inverse minus, so it's minus tan phi tan delta, or cos inverse, it will be minus tan phi minus beta and tan delta. Okay, so its mod value. Okay, so it should be independent of your the sign of the value we are getting. So this is the formula. This formula is also mentioned in the lecture slides also. So now let's take these two cases. Okay, let's add one more slide and see this question. Okay. So now for June 21, what we know is the formula we know, which is uh, let's put the value. So mod of omega st will be minimum of mod of cos inverse minus of tan phi. Your phi is your phi angle was, so your phi is 19 degree 7 minutes. Okay, so which we can convert into degree by dividing it by 60, and it will come to be 19.12 degree. Okay, so and your beta is 10 degree. So these two angles are what will be required. So we can write 19.12 degree, and tan delta is your 23 point, declination angle is 23.45, right? The next uh, value was cos inverse minus of tan phi minus beta. Okay, so phi is your 19.12 or beta is your 10 degree, right? And this is tan delta 23.45 degree. Okay, if we solve this, then you will get minimum of either this, the first term will come to be 98.6 degree and the second term will be 94.0 degree. So minimum is, out of these two value is 94 degree, and omega st value will be, if you remove this mod, it will be plus minus 94 degree. Okay, this is your final answer. Similarly for December 21, we can put all the values. So let me just write it quickly. So it will be minimum of mod of cos inverse minus tan. This will be 19.12. Tan, it will be now minus 23.45, right? The declination angle has changed, and then it will be minus of tan 19.12 minus 10 into 10 minus 23.45 degree, right? So the values will be minimum of 81.4 degree and 86 degree. So now here minimum value is 81.4, right? And your omega st value will be plus minus 81.4. So this is the, okay, so this is the our angle at sunrise and sunset. So that's why we have two values here, right? Plus and minus two values. So afternoon it will be negative and forenoon will be positive value, right? So we have calculated omega as sunrise and sunset value for a tilted surface for both June 21 and December 21. I hope this question is clear. Now this is the next question. Determine the local apparent time corresponding to 14:30 hour Indian Standard Time at a location of Mumbai on July 1st in India. Standard time is based on 82.50 degree east, which is passing through Prayagraj, right? So I'll give some time and then we'll see this question also. Okay, let's see this question also. So we have to calculate the local apparent time corresponding to the given clock time at Mumbai. The location, latitude and longitude is given on a certain day, and we know that the standard Indian standard time is based on this latitude. So let's see. So what's given in the question is your time mentioned is 14 hour 30 minutes with Indian standard time. Okay, and your longitude, standard longitude for India is 82 degree, and this is 50, right? And 82.50, this is east. Now the latitude of the local location, that is also given, which is your 72 degree 51 minutes. So we will first convert it in degree, which will be 72 point, it will come 85. Okay, so now we know that to calculate the local apparent time, we have one relation, which is standard time. Okay, so this is your standard time. So standard time, let me write it. Okay, plus minus 4 standard time longitude minus longitude of particular location, and plus equation of time correction, right? Where E value is given by, uh, there was a very long equation, 22.9.18 into 0.000075 plus 0.001868 cos B minus 0.032077 sin B minus 0.014615 cos 2B minus 0.04089 sin 2B. Okay, where B was n minus 1 upon, this will be 365 into 360. Here n value is for July 1st, right? July 1st you can calculate n value, which will be 31 plus, it will be 28 plus 31 plus 30, okay, plus 31 plus 30 plus 1. We'll add this and we'll get the value of n. Okay, and for this n, we'll put this one n value into to calculate B, and this B value will put in this E equation to get the value of E. Okay, so okay, so if you'll put all this value, you'll get the E value to be minus 3.5 minutes. Okay, now we can calculate the local apparent time. It will be 14 30 hours minus, so uh, in east we take minus direction, and if we go to west we take the positive direction, right? If you remember the sign convention. So the standard was 82.50, the location longitude was 72.85. Okay, this will be in minute, right? Plus E value, which was minus 3.5 minute. Okay, we'll solve this. Okay, it will be 1430 hour minus 38.6 minute and minus 3.5 minute. And further solve it, you can get the local apparent time to be this in hours. Okay, so this will be your final answer. Okay, so this was the basic question. Uh, this is the next question. Calculate the monthly average hourly radiation falling on a flat plate collector. So now we have seen all the question on the how to calculate the angles and all. Now we'll we have jumped on the flat plate collector questions. So this is a simple question based on flat plate collector where we have to calculate the monthly average hourly radiation falling on a flat plate collector facing south with a slope of 15 degree. Given the following data, the location, the month, the time, the average global radiation and the diffuse radiation is given in the question, along with the ground reflectivity. So I'll just wait for a few minutes and then we'll solve this question. Okay, let's see this question. So we have to calculate the monthly average hourly radiation. Okay, on a flat plate collector. So let's write first of the given values. Okay, so it's facing south. Azimuth angle is given 0. Slope is 15 degree. Okay, the location is given. So your phi value is given. It's 13 degree. The month is given of October. Okay, so for October, if you remember the N value for October, so we have an average day for a particular month, and it's a whole table given in the your lecture also. So uh, for October, it's the average day of the month is October 15th. Okay, and for October 15th, you can calculate the value of n, which will be say 31 plus 28 plus 31 plus 30. May, this is for June, July, August, September, okay, and October. So if we'll calculate it, the n value will come to be 288. Okay, now what else is given? Uh, your time is given. Okay, so the time mentioned here is 11 to 12. Okay, the average global radiation is given, which is 2408. kilojoule per meter square per hour. Okay, and the diffuse radiation is given 1.1073 kilojoule per meter square per hour, and ground reflectivity is given to be zero point 0.2. So these are the values already given in the question. Now what we need to find is monthly average hourly radiation. So first of all, calculate all the required angles. Yeah, for from this n we can calculate the declination angle, which will be 23.45. Okay. So you can write it at 360 by 365, 284 plus n, which will be 288. If we'll calculate this, your declination angle will be, it will come to be minus 9599 degree. Okay. So this is your declination angle. Now let's solve this. So first, you know that to calculate the average hourly radiation, what we are trying to calculate is IT value, right? IT basically bar. For a whole month we are trying to calculate. And we know the formula for this. It will be IB bar upon this will be basically capital RB. Okay. And this will be ID bar upon capital RD, and this will be IB bar plus ID bar, and this will be your capital R bar, right? Now to calculate this RB value, okay, so if we calculate it for October 15th, it will be same to the RB bar value, okay, right? Because we are calculating it for the average day of the month, right? So we'll calculate it. It will be we know that it is cos theta upon cos theta rate, right? So cos theta is your sine delta. This will be sine phi minus beta plus cos delta cos omega cos phi minus beta upon sine phi sine delta plus cos phi cos delta cos omega. Okay, so we'll put all the value. So it will be sine, it will be 9 minus 9.599 it was, and sine phi minus beta. So phi is your 13 minus 15, right? So it will be 13 degree minus 15 degree plus cos delta is minus 9.595, cos omega is, okay, first write this 13 minus 15 and then we'll see omega. So omega will be will take the average of this 11 and 12, which will be 1130, and corresponding to 1130 we know that it will be half of 15 degree, right? So it will be uh, plus 7.5 degree, right? It's 4 noon. So we'll put this value into cos 7.5 degree upon this will be sine phi is your it's okay. So phi was your 13, right? And delta is your minus 9.595, and cos phi is your 13, cos delta is 9 minus 9.595, and cos omega is your 7.5. If you solve this, you can get the value of RB bar, which will be 1.074. Similarly, we can calculate the for diffused uh, radiation. We can calculate the RD bar value, okay, which will be 1 plus cos beta by 2, which will be 1 plus cos beta is your angle is 10 was 15 degree, right? So this value will be 0.9830, and okay, and now we can calculate RR bar value, which will be, which is reflectivity of your, here ground is given, right? 1 minus cos beta by 2. So we can put the values 0.2 into 1 minus cos of 15 degree by 2, which will be equal to 0.0034. Okay, so we have all the values now. We can calculate the IT value, right? The radiation falling on the tensile surface, so average radiation, so it will be um, IB plus uh, ID bar RD bar plus, so this is IB plus ID, right? So this basically it's global radiation, right? RR bar. So if we'll divide, we'll just divide it, so it will write it like this. I'm just rearranging the formula, so it will be 1 minus ID bar upon IG bar, uh, RB bar plus ID bar upon IG bar, it will be RD bar plus, so it's capital RR bar. So we'll put all the values. So it will be 1 minus 1073 was the diffused and global value was 2408. Okay, and into RB 1.074. Okay, 1.074 plus 1073 upon 2408 into this value is 0.9836. Okay, 9830. So 0.9830 plus your 0.0034 is your RR bar value. If you solve this, you'll get 1.0369. Now for IT value, you'll just multiply it by IG bar and you'll get the value of 2497 kilojoule per meter square per hour. So this is your required answer. Okay. So this is the next question on the PV part. So I'll read this question. So consider a 100 centimeter square photovoltaic cell with a reverse saturation current of 10 to 12 ampere per centimeter square. In full sun, it produces a short circuit current of 40 milliampere per centimeter square at 25 degrees Celsius. Find the open circuit voltage at full sun and again for 50 degrees sunlight. Half of the sunlight, okay? And just plot a result. It should not, like, it might not be up to the scale, but just to have an understanding. Okay, so I'll just give few minutes. Okay, let's see this question. So we have a PV cell. So reverse saturation current is given in this is okay. So this is 10 to power minus 12. Okay. So this is ampere per centimeter square, and your area for PV cell is given 100 centimeter square. Okay, and short circuit current is also given your 40 milliampere per centimeter square. The temperature is 25 degrees Celsius. Okay, and we have been asked to calculate the open circuit voltage at two point. One is at full sun condition and one is at 50% sunlight condition, right? So for our given cell of particular area, the reverse saturation current of cell will be your I naught into your I naught will be 10 to power minus 12. This is ampere per centimeter square, and our cell area is 100 centimeter square, right? So it will be 10 to power minus 10 ampere, right? Similarly, your ISC value will be it is 40 milliampere. So 10 to power minus 3 ampere per centimeter square into 100 centimeter square. So this will be your values will be, so it will be 4 ampere, right? Now this is at full sun condition. So we know the formula for VOC, open circuit voltage. If you remember the formula, it is 0.0257, and then this will be ISC, short circuit current upon saturation current, reverse saturation current plus 1. Okay, so we know all the values, we'll put the values. So it will be 0.0257. ISC value is your 4, and I naught value is your 10 to power minus 10 plus 1. So this will be 0.627 volt. Okay. Now we know that the short circuit current value is directly proportional to your uh, intensity, solar intensity, right? Greater will be the intensity, more will be the value of your short circuit current. So if you talk about at half your sun, or you can say 50% of incoming solar radiation, your ISC value will now will be new ISC value will be half of the value, right? The previous value, so the previous value was 4, right? So it will be now 2 ampere, right? So if we'll calculate the VOC now, it will be 0.0257 log of, now it will be ISC dash will be your 2 ampere upon reverse saturation current was your 10 to power minus 10, right? Plus 1, and it will be 0.610. Now if we'll plot these two values, okay, so um, okay, let's take it on the next page. So this is your voltage and this is your current, I versus V plot. If you plot it, let's say it's 1, 2, 3, 4, and here we have some values, 0.1, point say 3, 0.5, point 0.6. Okay, similar values. So at if you want to draw the at full sun condition, okay, so the your ISC value was 4, right? Short circuit current value was 4 ampere, and your VOC value calculated was 0.627. Okay, so the graph will be, say, 0.627 will be somewhere here. So the graph will be like this, right? This will be at full sun condition. Okay, and your VOC will be 0.627, and your ISC current value will be 4 ampere. Now, in the half sun condition, if you plot the graph, the ISC value was, so ISC dash value was now 2 ampere, right? And you will note the VOC value is not 0.610. Okay, so say here. So this will be the plot. Okay, so you can clearly see that as we decrease the solar intensity, there is a very profound effect on your short circuit current value, but the open circuit voltage value have not as much difference or the effect with the as compared to the short circuit current with the change in intensity of the incoming solar radiation. Okay, so now this was the question on the PV. Okay. Now this is another question on solar PV and lamp. So I'll read this question aloud. So in a solar PV LED lamp operating at a voltage of 3.2 volt DC current and draws a current of 0.15 ampere, the lamp is required to operate for 5 hours every night. Assuming that the configuration your your PV LED configuration is used, calculate the wattage, power, and the area of the PV module required, which would collect enough energy through the day and operate satisfactorily at night through the year. Also calculate the capacity of the battery. If the battery voltage is 2.4 volts and the depth of discharge is 80%. What else is given? The daily global radiation varies from minimum of 4 kilowatt hour per meter square to 7 kilowatt per meter square depending on winter and summer, right? And the PV module efficiency is given. The battery charging efficiency, discharging efficiency is given along with the LED driver efficiency. Okay, so I'll just wait for a few minutes and then we'll solve this question. Okay, let's see this question. Solar PV LED lamp system is there. So the voltage is given 3.2 volt and the current drawn is 0.15 ampere. Okay, the lamp is required to operate for 5 hour every night. So the time is 5 hour per day, right? Now calculate the wattage and the area of the PV required to collect energy throughout the day and operate satisfactorily at night throughout the year. So we have been asked to calculate for a year what will be the power and the area required to meet our load requirement. Now what else is given? The battery voltage of the battery is given 2.4 volt and the depth of discharge is given 80%. Other than that, your global radiation was given 4 kilowatt hour per meter square in. This is in winter, and in summer it's 7 kilowatt hour per meter square. Okay. Now the PV module efficiency is given, which is 15%. Battery discharging efficiency. So the charging efficiency is given 95%. Discharging efficiency is given 93%, and your LED efficiency is given 85%. Okay, so let's solve this question also. So for LED lamp, the voltage and the current value is given. So we can calculate the power of LED lamp, right? Which will be V into I, which will be 3.2 into your current value was 0.15. Okay, so it will be 0.48 watt. Now this has to be operated for 5 hours every night. So if you want to calculate what is the energy consumed by lamp in 5 hours, then it will be your this value multiplied by 5. So it's for so we'll get the value. It will be 2.4 watt hour per day, right? Now if we consider the driver efficiency, so LED driver efficiency is given. So the actual energy consumed, considering your driver efficiency, it will be this 2.4 divided by your 85%. Okay, so it will be 0.85. So this value will be 2.824 watt hour per day. Now the PV module needs to supply enough energy to the battery, and which in turn will supply the required energy to the load, right? So we have a battery, right? So this should produce enough power that will be stored in battery and will be provided to LED at the night. So this is the whole concept. So the required input energy of the to the battery for a particular day we can also calculate, right? So if we calculate the required input energy to battery in a particular day, if you're trying to calculate, it will be your output energy from the battery. So your output energy from the battery is what is going into the your LED lamp, right? So which will be equal to this value that we have just calculated. So it will be 2.824. Now we will now consider the charging and discharging efficiency of the battery also, right? So which is 93 and 95%. So we will divide it by 0.95 and 0.93. So this value will become to be 3.196 watt hour per day. So this is the actual energy input that is required uh, to be fed into the battery for our load requirement. Okay. Now, if you remember, the PV module rating is done at the standard value of solar global radiation of 1000 watt per meter square, right? If the cell is maintained at a temperature of 25 degrees Celsius, so standard testing condition, it's 1000 watt per meter square at 25 degrees Celsius, right? Now, we have given the daily minimum global radiation of 4 kilowatt hour per meter square, and this can be interpreted as 1000 watt per meter square available for 4 hour per day, right? So if we have 4000 uh, kilowatt hour per meter square, it could be interpreted as it's 1000 your watt per meter square for 4 hours, right, per day. It could be interpreted, so if we want to calculate the PV module wattage that is required, that will be the value we just got, okay, divided by this 4. So it will be in watt power. Okay, so it will be in 0.80 watt power. So this is the required what is for the PV module. Now, next is to calculate the area. Okay, so let the area of PV module, this be your, say, a meter square. Okay, now we assume that the module efficiency was given 15% is valid through the day, even though the global radiation is varying throughout the day, so it does not affect the module efficiency, it's constant to be 15%. Now, uh, but the PV, we have to also consider that the PV module temperature is also going to be higher than 25 degrees Celsius, which is different than what we assume at standard test condition. So for that, there will be some power loss. To basically account for that loss, we are just we'll be multiplying the loss in efficiency to consider that by the factor of, say, 0.90. Okay, so if we consider that, so the PV what is that module what is that we have calculated, or so, or the input energy to the battery that we have calculated, 3.196, it was 3.196 watt hour per day, that should be equal to uh, your area, your incident flux onto your module, so which will be 4 into 1000, right, into your area of the module, into your module efficiency, which was 0.15, and we are considering some loss due to the increased temperature of the PV module. For that, we are considering a factor of 0.9. Okay, so this is your energy balance, right? So if we consider that this is the energy balance, whatever is produced considering the module efficiency, it should be equal to the required input energy to the battery for a particular day. So if you solve this, your area will be 5.92 into 10 to power minus 3 meter square, or just to understand it, 59.2 centimeter square will be the your required area. Now, okay, so we have calculated the area, we have calculated the wattage. We can also calculate the capacity of the battery. Okay, so the capacity of the battery, it will be energy consumed upon your battery voltage into your battery discharge efficiency into your depth of discharge. Okay, so your energy consumed was, so this value was your 2.824, right? So this was 2.824. Battery voltage was 2.4 volt, and discharge efficiency was 93%. So, and depth of discharge was 80%. So let's put all the values. So it will be 2.4 volt, it will be 0.93, and depth of discharge was 80%. So it will be in ampere hour. Okay. So if we'll solve this, it will be 1.58 ampere hour. This will be the capacity of the battery. Okay. So in order to charge the battery safely, the difference in voltage between the PV module and the battery typically should not be greater than 1.5 volt. Okay. So this value is typically specified with by the manufacturer of the battery, but this is all the uh, parameters that has been asked. We have calculated it, and we have understood how this PV module is basically applied in actual scenarios. Okay, now this is the next question. I'll read this question aloud. So we have a flat plate collector. So now this is question on flat plate collector. Okay, which is made up of copper absorber plate, copper tube fixed on underside, and one glass cover. Okay. The following data is given: length, width of collector, length of absorber plate, width of absorber plate, plate to cover spacing, thermal conductivity of plate material, its thickness, absorptivity for solar radiation, emissivity for irradiation, outer diameter of the tube, inner diameter of the tube. So uh, I'll just draw this figure so it will be easier for you to calculate. So this is a flat plate collector. Okay. Okay. Or underneath is your copper tube fix. Okay. So this is your glass cover, and this is your absorber plate, and this is your copper tube. Okay. Now the length and width of the collector is given. So this is given 2.08 meter, and the width is given 1.07 meter. The length of the absorber plate is given, which is 2 meter, and the width is given 0.98 meter. Okay, so this width is given 0.98 meter. The plate to cover spacing, this value is given 2.5 centimeter. So it's in centimeter, right? The thermal conductivity of the plate is given, which is 350 watt per meter Kelvin. Plate thickness is given, which is 0.15 mm. What else is given? The plate absorptivity for the solar radiation is 0.94. Emissivity is given 0.14. Okay. Now this tube, the tube outer dia is given. So this is 13.7 mm. Inner dia is given 11 point, okay, 12.5. Tube center to center distance. So this value is given. This value is given uh, 11.3 centimeter. Other than that, glass cover emissivity and absorptivity is given. This glass cover emissivity and absorptivity is given, which is equal to your 0.88. Extinction coefficient of glass is given. Thickness of the glass cover is given. This is 4 mm. Refractive index is given, and the date, time, collector tilt is equal to the latitude angle, surface azimuth angle, beam radiation, diffuse radiation, adhesive resistance is negligible, fluid to heat tube heat transfer coefficient. So this is given. Water flow rate is given. Okay, water inlet temperature is given. Ambient temperature is given. Wind speed is given. Back insulation thickness is given. Insulation thermal conductivity is given. Reflectivity of the surrounding surface is given. And we have to calculate the angle of incidence of beam radiation on the collector, total solar flux incident on the collector, the tau alpha for beam and diffuse radiation, the incident flux absorbed by the absorber plate, the collector heat removal factor, overall loss coefficient, water outlet temperature, and instantaneous efficiency. So it's a very uh, cumulative question of all the important parameters that need to be calculated for a flat plate collector. Okay, so I'll just give few minutes and then we'll start solving this question. Okay, let's see this question. So the day that has been mentioned is May 15th, right? So let's start from here. We'll first calculate. First question was to calculate angle of incidence, right? Of beam radiation. To calculate it, we know first need to know all the angles, right? So the day was mentioned was May 15th. So and for May 15th will be your 135. Directly we can calculate the declination angle, which will be 23.45 sine 360 by 365 to 84 plus and n is your 135. Right? So your declination angle will be 18.79 degree. Okay. Now, what else is given in question is the time is 12 o'clock noon. That is your standard time given. IST time, Indian Standard Time is given, right? So first we need to calculate. Actually, we want to calculate the hour angle. So to calculate hour angle, first we need to know the local apparent time, right? So we'll calculate local apparent time, okay, which is 12 hour minus. So minus because we are we are taking sign convention for east, it will be negative, right? So it will be 73.51 degree, and your standard is your 82.5, right? So for India, standard is 82.5. So let me write first. So 82.5 degree is standard longitude, and for the location it is 73 degree 51 minutes. So it will be 73 plus your 51 by 60. Okay. So it will come to be 73.85. Okay. We have just recently used this number 73.85. Okay. This will be in minute plus your E. E, we know how to calculate E. E will be your long equation, which is a function of B value, where B value was, um, if we remember, the B value was n minus 1 by 360 by 365 n minus 1, right? So we'll calculate this B value, and by putting this n135 value into this particular to calculate this B value and put back into this equation. I've already calculated this. This E value will be it will be plus 2.6 minutes. Okay, so we'll put this value here and we'll calculate the local apparent time. Okay, this will be 12 hour minus 32 minutes, which will be finally 11 hour 28 minutes. It will be your local apparent time. Okay, so from 12 o'clock noon local apparent time, if we want to calculate our angle for this particular uh, time, then we what we have to do is, so we know that for 1 hour is equivalent to 15 degree, right? So 60 minute is equivalent to 15 degree, right? So let me write. So 60 minute is equivalent to 15 degree, right? So from 12 o'clock, this time difference will be your 32 minutes, right? So we will calculate with respect to 32 minutes. So it will be 15 by 60 for 1 minute, and for 32 minutes it will be, this value will be 8 degree. So this will be your hour angle. So we have calculated declination angle, we have calculated hour angle. Now we know the cos theta value, right? So cos theta value we can already calculate. So okay, so for tilted angle, so the tilt angle first we'll see. Okay, let's see the tilt angle. So the tilt angle was given to be, okay, so somewhere, let's say, okay, first we see that the surface azimuth angle was 0 degree and your collector tilt angle was given equal to your latitude angle. Okay, so basically what it has been mentioned is your phi is equal to beta. Okay, your tilt angle is equal to your latitude angle. So if you write the formula for cos theta value in case of a tilted surface facing south, where we will put gamma equal to 0, if you put this, if you remember this formula, it's sine delta. This will be sine phi minus beta. Okay, so this will be sine delta sine phi minus beta. It will be cos delta cos omega cos phi minus beta. Okay, so this will be, we know that sine delta value is your 18.79, right? So it will be 18.79 degree, and phi and beta value are equal, so it will be sine 0. Okay, and cos delta will be 18.79, cos omega will be, omega is 8 degree, right? So it will be 8 and this will be cos 0. So cos 0 sine 0 will be 0, so this will be cancelled. So the your theta will be finally, cos theta, this value will be 0.9375 and your theta value will come to be 20.36 degree. So this is the angle of incident for beam radiation on your tilted surface. Okay, now if you want to calculate the solar flux incident on the collector, okay, so solar flux incident on the collector. So first we need to calculate the R value for beam diffused and your reflected, right? So RB value we know that it's cos theta upon cos theta z, right? Cos theta we have already calculated. It's your 0.9375. Cos theta z is for your horizontal surface. So it will be simply your sine delta. Sine delta is 18.79 into sine phi. Sine phi is your phi value was okay 18.32. So it will be converted. It will be 18.53. Okay, plus cos delta, cos omega, and cos this phi. If you solve this, you will get the RB value to be 0.9458. Similarly, we can calculate for diffuse radiation R value. So it will be 1 plus cos beta by 2. Beta is your equal to your 18.53 or 5. So it will be cos 18.53 divided by 2, which will be equal to 0.9741. And your R value will be rho. Rho is your reflectivity, which is given to be, I think, zero point 0.2. So it's given zero point 0.2. So zero point 0.2 into 1 plus 1 minus cos beta. So it will be cos 18.53 divided by 2, which will be equal to 0.0052. So now we can directly calculate the total flux falling on a inclined surface. Your collector, it will be your IBRB plus IDRD plus IB plus ID into RR. So we'll put all the values. So it will be, so beam radiation was 725 and diffuse was 230. So it will be 725 into your RB value was, okay, so it was 0.9458 plus 230 into 0.9741 plus 955 into 0.0052, which will be equal to 914.7 watt per meter square. So it's actual flux falling on your solar panel, your sorry, flat plate collector. Now, if you want to calculate the tau alpha for beam and tau alpha for diffuse radiation, how will you calculate it? So we know the angle of incidence, which is equal to your 20.36, right? So we know the theta 1 value, which is 20.36. Angle of refraction we can calculate. So we know the Snell's formula. Well, n2 by n1 was your sine theta 2, theta 1 by sine theta 2, right? So from here we can calculate your theta 2 angle, which will be your equal to sine inverse. This will be your sine of 20.36 divided by refractive index. So it will be 1.526. So your theta 2 value will, after solving, will come to be 13.18 degree. Now, if you remember, we have solved similar questions. So first we need to calculate the different component of your reflected rays. So your rho 1 and rho 2, which formula, sine square, it's theta 1 minus theta 2 upon sine square theta 1 plus theta 2, and rho 2 was the second component was tan square, it's theta 1 minus theta 2 upon tan square theta 1 plus theta 2. So these two values, if you put this value, it will be 0.0512 and it will be 0.0361. So we know the rho 1 and rho 2. We can calculate the transmitted due to reflection and reflection. These two component. Okay. So which was 1 minus, this was rho 1 upon 1 plus, this is rho 1. And this will, this, if we'll put this value, it will be your 0.903. So it's 0.903, and we can calculate the second component, which was 1 minus rho 2 upon 1 plus rho 2, and this will come to be 0.930. So now we've calculated all the two component for reflection and trans. Okay, so let me add some more slides to solve this question. Okay, so now we can calculate the transmittivity due to refraction and reflection only. So this, we calculated the tau r1 and tau r2 value, the two component. We can add this two and take its average. So if we'll do this, this will be your 0.903 plus 0.930 divided by 2, and it will be your 0.9165. So you had calculated the transmittivity due to the refraction and reflection also. Now due to only absorption, if we want to calculate, you might remember another formula where it will be e to power. So it will be e to power minus, if I remember the formula. Okay, so okay, right. So it e to power minus k delta c into cos theta 2. It was the formula. Okay, so we know the value of k, right? So k value is your 19. Okay, extinction coefficient of the glass, and the thickness of glass is 4 mm. Okay, so we'll put all the values. So it will be minus 19 into 4 mm. So we'll put in meter, divided by your cos theta 2. Theta 2 value was, I think, 13.18. Okay, this will be, if we'll solve this tau a value will be come to be 0.925. Now the transmittivity is both due to the refraction and reflection and due to your absorption. So the total transmittivity of the glass cover will be multiplication of these two values, okay, which will be equal to zero point 0.9, okay, it will be 0.848. Okay, so this we have calculated for beam radiation. Okay, now to calculate, now we can calculate similarly for diffuse radiation also. But let me first calculate this tau alpha b value directly for beam, tau alpha value for average, tau alpha value for beam radiation. So the formula was tau into, this was absorptivity, into 1 minus alpha into tau. Sorry, it's rho d. Okay. So if we'll put the value, tau value is 0.848. Absorptivity value was, okay, so it was 0.94, right? And right, so let me put the value. So it will be 0.94, 1 minus 0.94, and rho d value. Okay, so the rho d value we have to calculate, and that, okay, so this value we need to calculate. So for that we will first go for the diffuse radiation. So for diffuse radiation, the angle of incidence that we assume is 60 degrees. Okay, so let me solve it on the next page. So for diffuse radiation, theta 1 is taken to be 60 degree. We can similarly calculate the theta 2 value by the Snell's law. Okay, so it will be sine inverse, this will be now sine 60 upon your refractive index. It will be 1.526, and this theta 2 value will be now uh, 34.58 degree. Okay, so similarly we'll calculate all this row 1 row 2 value. I will just write these values because I have calculated it, so I'll just directly write these value. The process is similar to what we have done for beam radiation. So tau r1 value is 0.6872 and tau r2 value is 0.9972, and then we will calculate the average of these two value to get your tau r value, which will be equal to your 0.8422, and then we'll calculate your tau a value, which is due to absorptivity, which will be e to power minus, this will be your again 19 into 0.004 was the thickness of the glass and extension coefficient, and cos theta 2, so theta 2 is 34.58, so this value will come to be 0.912. Okay, now we can calculate tau, which will be tau r into tau a, right? So which will be 0.8422 into 0.912, which will come to be 0.768. So we have calculated all the required values for direct and diffuse radiation. Now this rho d value is actually what? So your rho d value is tau a minus your this tau, right? So which will be 0.912 minus 0.768, which will be 0.144. This value we put here 0.144, and this value we can get, we'll solve this value, and this value will become to be 0.804. Okay, this is your answer. And similarly we'll calculate for diffuse radiation, which will be tau alpha, which will be your 0.768. Okay, so the formula, we'll put all the value, it will be 0.768, this tau value, into your 0.94 alpha value, 1 minus 1 minus alpha into rho d, and this value will be 0.728. So we have calculated the properties of the glass material. Now if you want to calculate what is the incident flux that is absorbed by the absorber plates after passing through this glass cover, then we can directly calculate after getting all this value. Okay, so it will be your IB into RB into tau alpha for beam radiation, and this will be ID into RD into tau alpha for diffuse radiation, right? So we'll put all the values, it will be 725 into, it will be 0.9458 into, this will be 0.804 plus ID value is 230 into 0.9741 plus 0.728. This will be IG into RR into, okay, so this will be okay, this will be tau alpha D. So this will be 955 into 0.0052 into 0.728. We'll solve this value and we'll get the value to be 718 watt per meter square. So this is the actual flux that is absorbed by the absorber plate. Okay, so we are way beyond our 2 hour limit of this session. So what I will do is I will post the solution of this question in the uploaded slides, and you can look back to this solution. So this is the solution until you calculate your incident flux absorbed by the absorber plate. Okay. The next I can upload it in the slide, and will upload on your the link that had been provided for you for this live session. Okay. So thank you all for listening. Uh, we will end this session now. Thank you.